Okay, so in this video, we will consider lines in R3 and how to parameterize them. And then we'll consider an example of a distance between a point and a line in R3. And we'll look at two different solutions. So the first question is, how would you describe a unique line in R3? Well, as you know, you only need 2 points. Take any 2 points in three-dimensional space, and you can pass through these 2 points a unique line. So let's visualize this. Imagine a line, and all you need, so this line again doesn't have to be in the xy plane, it could be in 3 dimensions. And if you give me 2 points in space, let's say P0 and P1, I can pass a unique line through these 2 points. The question is now, how do we describe every other point of this line? Because to begin with, we only have 2 points, P0 and P1 in space. We pass the line through these 2 points, we have a unique line. And how do we find every other point on this line? Call this line L. Well, the idea is to form a vector with P0 and P1. This vector will be parallel to the line. Let's call this vector V. So V is a vector P0, P1. And as always, if you wanted the coordinates of vector V, you would do the terminal point minus the initial point. That'd be P1 minus P0. Suppose that P0 has coordinates x0, y0, z0, and P1, x1, y1, z1. Now imagine how you could build every other point on this line using P0 as your anchor and V as the directional vector of the line. Let's do a few calculations here to see how we can get every point on this line, and this is how we will parameterize the line L. So suppose I do P0 plus V. Well, which point do I get? Well, I'm starting at P0, P0, and I'm adding V, so I get the point P1. So I get this point now. What if I did P0 plus 1/2 of V? Well, I'm starting at P0, and I add a half of V, so I get this point. What if I did P0 plus 1/3 of V? Well, I would get, starting at P0, adding 1/3 of V, you'd get about here, you'd get this point. What if I did P0 plus 2 times V? Well, add to P0, not just V once, but V twice, and you'll get this point. And what if I added, say, P0 plus minus of V? Well, now I'm starting at P0, and I'm adding the vector whose length is V, but in the opposite direction, so I would land right here. And you see where this is going. If we add to P0 every possible multiple of V, we will get every single point on this line. And that's how we parameterize the line. So take any point on the line, P0, and that point again can be any point on the line, and all you need is the directional vector of the line, that is, any vector that is parallel to the line. And if you add to your anchor point, P0, all possible multiples of the vector V, so T ranges over all possible real numbers. If you add to your anchor point P0 all possible multiples of the vector V, you will get every single point on this line, and this is a parameterization. This form is called the vector form of the line. So all you need to describe a line explicitly in R3 is any point on the line and any vector is non-zero that is parallel to the line. And if you add to your anchor point every possible real multiple of the vector v, you will get every point on the line. Now there's one more form that's useful, and this is the so-called parametric equations. What if we collapsed this equation into a single point? So we have our point P naught, and the vector v, suppose has coordinates v1, v2, and v3, whatever they may be. Let's just compute now P naught plus TV. And what do we get? Well, the point P naught is x naught, y naught, z naught, plus t times v, but if you multiply a vector or a point by a real number, you multiply all of its coordinates, so t v1, t v2, t v3, and you add points by adding the corresponding coordinates, so you'll get the point x naught plus t v1, y naught plus t v2, and z naught plus t v3. And this is now expressing the point P naught plus TV as a single point in space. And if you look, this is your x coordinate of your point. This is the y coordinate of your point. And this is the z coordinate of your point. And these are the so-called parametric equations of the line. And so we can write the line in yet a different form. We write L colon. So the line is given by the following so-called parametric equations. X is given by x naught plus t v1. Y is given by y naught plus t v2. And z is given by z naught plus t v3, where we can specify that t ranges over all possible real numbers. And these are called the parametric equations. And why parametric? Because we have parameterized the x, y, and z components of our point. And you see, if you want to go from this form of the line to the vector form, P naught plus TV, all you need again is the point P naught and the vector v. Well, the point P naught is any point on the line, so for any given value of t, you get a point on the line, so pick t to be 0. And you get the point x0, y0, z0. And you see that the vector, the directional vector of the line, are the coordinates that are multiplied by t. So multiple of t here is v1, multiple of t here is v2, multiple of t here is v3. Hence, v1, v2, v3 are the coordinates of your directional vector. This is how you can go back and forth between the vector form of a line to the parametric equations of the line. And you'll see in some problems, one form is better than the other. And that's it. This is how you describe a line in three-dimensional space. There's nothing more going on. All you need is one point on the line, one vector parallel to it. Now let's consider an example of a distance problem between a line in R3 and a point in R3. And we will solve this problem using two different methods. So here's what we want to find, the question. We will take a point on a line, say point P0 and line L, and we want the distance between this point and the line. Where? Well, what is the point? What is the line? The point P0, or P naught, will take to have coordinates 2, 1, negative 1. And the line will give in vector form 1, negative 2, 3. This is the point, our anchor point, plus t times, this is now our directional vector, 4, 1, 1. And we can drop the t ranging over all real values. This will always be implicit. Every time you write the vector form of a line or the parametric equations, the parameter t always implicitly will range over all possible real values. So as always, this is our anchor point. We could call it P. And this is our directional vector of the line. Let's call this V. So we have this line in three-dimensional space. We have the point P naught, and we want the distance between P naught and the line L. As always, whenever you have a distance problem, you have to make sure that the problem is not trivial. What do I mean by trivial? Well, what if the point P naught was a point on the line? Then the distance would be 0 and would be done. So let's check that the problem is not trivial, that P naught is not a point on this line. And this will be very easy to see if we rewrite the line in its parametric equations form. So let's do this. X will be 1 plus 4t. Y will be negative 2 plus t. And z will be 3 plus t, where again t can range over all real numbers. And now think of it. If this point were a point on the line, there would have to be a choice of t that would give us this point. Look, for example, at the y component. The y component is 1, and on the line it's negative 2 plus t. If this were equal to 1, t would have to be 3. 3 minus 2 is 1, check. But if t is 3, the z component is 3 plus 3, which is 6, which is not negative 1. So you see it's impossible to find a value of t that will give us this point. Hence, the point P naught is not a point on the line. So we'll have a positive distance. So now we have a non-trivial problem. As with every problem of distance, we always want to visualize the situation. What we have is a line and the point is not on the line, and you don't need to have an accurate picture of this line and this point in the three-dimensional coordinate system. All you have to think of is I have one line and one point, and the point is not on this line, so you can draw a very generic picture. So imagine that we will visualize our line this way, and suppose that the point P naught is here. The coordinates of P naught are 2, 1, negative 1. And now, when we draw our line, always include the two defining objects of this line, being the point on the line and the directional vector. Now, the point on the line could be anywhere on the line. Just for convenience, I'll draw it, say, here. This is the point P, and it has coordinates 1, negative 2, 3. And the vector v has the property of being parallel to the line. We don't know how long it is with respect to this picture. It may be much longer or much shorter. So let's suppose that it is, say, this long. Again, it doesn't matter. But suppose this is our vector v, imagining that P is its initial point. And the coordinates of our vector are 4, 1, 1. The question is now that we have included all key elements, the line with its anchor point and its directional vector, and the point P naught, how do we find the distance between this point and the line? As always, visualize the line segment whose length is the distance. Well, that would mean connecting P naught with the line L in a orthogonal fashion. And the length of this segment is our distance, right? This is our distance. Now, let's find or produce two different solutions to this problem. Now, a natural idea here is to connect P and P naught to form the vector P, P naught. Let's do so. And I will call this vector vector U. As always, if you want the coordinates of a vector, you do the terminal point minus the initial point. So 2 minus 1 is 1. 1, negative, negative 2 is positive 3. And negative 1, negative 3 is negative 4. And we now have the coordinates of vector u. 1, 3, negative 4. And now we're good to go. We have everything we need to produce two different solutions. So let's begin with the first solution. So solution 1. In this solution, we are going to use the orthogonal projection. So imagine projecting vector u in an orthogonal fashion onto vector v. You would then obtain this vector, which we'll call w1, and that is the orthogonal projection of u onto the vector v, the vector parallel to the line. And of course, we now have the orthogonal complement, w2. And if you notice, the distance between the point P naught and the line is simply the length of w2. So that's what we want. The distance will be the norm of vector w2. So if we can find this vector, we find its norm, and we're done. Well, let us first find the projection vector w1. So w1, as we've just said, is the orthogonal projection of u onto the line, therefore onto vector v. Recall the formula for the orthogonal projection. It is u dot v over v dot v. That is the scalar multiple of vector v. Well, u dot v. V dot v, let's compute both here. When we dot two vectors, we multiply corresponding entries and we add them up. So 1 times 4, 4, plus 3 times 1 plus 3, plus negative 4 times 1, negative 4, and we're left with positive 3. V dot v will be the sum of the entries squared. So 4 squared plus 1 plus 1. So 16 plus 1 plus 1 gives us 18. So this is just 3 over 18 times the vector v, which is 4, 1, 1. We can simplify. 3 over 18 is just 1 over 6. So the vector w1 is 1 over 6 times 4, 1, 1. And now think of it. We have vector u. We have vector w1. How do we get w2? Well, quite simply, w1 plus w2 equals u. And so u is w1 plus w2. Therefore, u minus w1 is w2. Let's compute this. So u was the vector 1, 3, negative 4, minus the vector w1, which is this vector, the sixth of 4, 1, 1. If you want to combine these two as a single vector, you have to have this vector over 6, so do times 6 over 6, equals 1 over 6. And now multiply this out. You'll have 6 minus 4 gives you 2. 18 minus 1 is 17. And finally, 6 times negative 4, negative 24, negative 1, negative 25. And now you have w2. And now, the distance is the norm of this vector. So let's compute the norm of this vector, and we'll have the distance. which will be our first solution. This is the norm of W2, the norm of the vector 1 over 6 times 2, 17, negative 25. As always, don't bring this into the vector and then find the norm. Factor the 1 over 6 outside. So 1 over 6 times the norm of the vector 2, 17, negative 25. And once again, here we use Pythagoras' theorem. The norm of a vector is the square root of the sum of the entries squared. So we'll have 1 over 6 times the root of 2 squared plus 17 squared plus, if you square negative 25, it becomes positive 25 squared. And if you compute this, 2 squared plus 17 squared plus 25 squared, you'll get 918 over 6. Now, if you factor 918, you can factor it as 9 times 102. This is root of 9 times root of 102, but root of 9 is 3. So you get 3 over 6 root of 102, but 3 over 6 is 1/2, and you're left with the root of 102 over 2 as the exact distance between the point P0 and the line L. If you want, you can use your calculator here to get an approximation, to get a feeling for how large or small the distance actually is. And the root of 102 over 2 is approximately 5.05. So you see we have a beautifully simple solution. We formed vector u from P and P0. We projected vector u onto vector v onto the line. Once we add W1, W2, the orthogonal component, was simply u minus W1. And once we had this vector, the norm of the vector was simply the distance. And that's it. So a really nice solution using, of course, a clear picture and orthogonal projections. I want to show you now a second solution using, instead of orthogonal projections, using the cross product. So look at this now, and I'll reproduce the picture, and then we'll start from, not from scratch, but almost from scratch. This is solution 2 using the cross product. And of course, you can use either solution, whichever you prefer. So, we had our line. We had the point P, given by 1, negative 2, 3. We had the vector V, parallel to the line, given by 4, 1, 1. This is the line L. Then we had point P0, given by coordinates 2, 1, negative 1. We had formed the vector P, P0, and we call this vector vector u. The coordinates of u were 1, 3, negative 4. And as always, we draw the distance, the line segment connecting the point P0 and the line L in a 90-degree angle, and the distance is the length of this segment. Let me now introduce the angle between u and v. And now I can connect the angle with the distance and the vector u using sine of theta. Right? Sine of theta, SOHCAHTOA, sine is the opposite d over the hypotenuse, which is the length of vector u. Therefore, the implication is that the distance is the norm of u sine of theta. Now, if I leave it like this, it's not so useful. Let me be sneaky here. Let me multiply top and bottom by the length of vector v. So I will do norm of u times norm of v sine of theta. Of course, now I'm cheating. I have changed the expression. I have to divide through by norm of v. And here where it's interesting. Norm of u, norm of v sine of theta, but theta is the angle between u and v. And if you remember, the norm of u times the norm of v times the sine of the angle between u and v is just the norm of the cross product between u and v. And now we're good to go because we know vector u, we know vector v, find their cross product, and the norm of u cross v over norm of v is our distance. And hopefully we'll get root of 102 over 2 as in the first solution. Let's see. Norm of v, let's find this first. This is rather easy, right? The norm of v is the square root of the sum of the entries squared. So 4 squared is 16, plus 1 plus 1. That's just the root of 18. Done. Let's cross u and v and see what we get. So u crossed with v is the determinant ijk. Second row is u, third row is v, so the second row is 1, 3, negative 4. Third row is v, 4, 1, 1. All right, so the first entry is C11, delete row 1, column 1. You get 3 minus negative 4, 3 plus 4 is 7. C12, be careful, we'll have to negate our determinant. Delete row 1, column 2, 1 times 1, 1, minus 4 times negative 4 is negative 16. 1 plus 16 is 17, but it is C11, so negative 17. And finally, C13, delete row 1, column 3. 1 minus 4 times 3, 12. 1 minus 12 is negative 11. So there you have it. You have u cross v, and all you want is the norm of u cross v. And this is, well, very easy. Once again, by Pythagoras' theorem, the norm of u cross v is the root of the sum of the entries squared. So you have the root of 7 squared plus 17 squared. You can drop the negative because when you square, you kill the negative. Plus 11 squared. If you compute this, this will give you the root of 459. And now let's go back to this expression, which was our distance. The norm of the cross product between u and v over the norm of v. And let's see what we get. The distance is the norm of the cross product, which is the root of 459, over the norm of v, which we found to be, quite simply, root of 18. Let's factor a little bit. This is the root of 459 over 18, but 18 is 9 times 2. If you divide 459 by 9, what you get is simply 51. So you'll have the root of 51 over 2. If you split those two up, you'll have the root of 51 over the root of 2. If you want to rationalize, multiply top and bottom by root of 2 over root of 2. And you'll get, well, the root of 51 times root of 2 is the root of 2 times 51, which is 102. Over root of 2 times root of 2, which is simply 2. Aha! So as before, the distance was found to be root of 102 over 2, which we found to be approximately 5.05. So you see, both solutions are very elegant. This one's a bit more subtle, but once you realize that you're close to the cross product here, the norm of the cross product, you just make it happen, and then you're good to go. So it seems that as far as the distance goes, both solutions with the orthogonal projection or with the cross product are basically equivalent as solutions. One thing is worth mentioning though. There is, in one respect, a reason why this solution is slightly weaker than the solution using orthogonal projections. What if I asked you from this solution to give me the point on the line L that lies closest to the point P naught? If you think of it, this is the point lying right here. Let me call this point Q. Look at what we have constructed in this solution. All we had from the beginning was vector v, vector u, and we don't have any other vectors here. All we did was the norm of the cross product and the norm of v, and we found the distance, but we don't have anything from this solution that would allow us to find the point Q directly. We're missing this vector and this vector, and that is a shortcoming of this solution. Let's go back now to solution 1 and find that there are two really easy ways to find the point Q. This is what we had from solution 1, and we had found both vectors w1 and w2 explicitly. And now think of how we can find the point on L that lies closest to the point P naught in two different ways. But at this point, both are very easy. Think of the first way, Q. What if you start at the point P? And now think of it, if you're standing here on point P, and you add to P vector w1, you land exactly on Q. I will leave the calculations to you. The point P was 1, negative 2, 3, and the vector w1 we found to be 1 over 6, 4, 1, 1. So add these two, and you get Q. You're done. Or, what if you were standing on P naught? And you wanted to walk from P naught to Q. Well, think of it. The vector w2 has the right length in the right direction. But of course, if you do P naught plus w2, you'll land way over here. But if you do P naught minus w2, you'll land exactly on point Q. Either case, you'll find the coordinates of the point Q lying on the line closest to the point P naught. And this is why, in some respect, this solution with the orthogonal projection is slightly better than the one with the cross product. Because if what you want is not only the distance between the point P naught and the line L, but also the point on the line L, say Q, lying closest to P naught, the solution is trivial once you have the projection and the orthogonal component. This will take you just one line. But if you find the distance between the point P naught and the line L using the cross product, once again, a very elegant solution. But if you wanted on top of that the coordinates of point Q, you'd be at a loss because you're missing these two vectors. And that is a shortcoming of this solution. So keep this in mind. If you only care about the distance between the point P naught and the line L, use either the orthogonal projection method or the cross product. Both solutions are equivalent and they're more or less the same amount of work. But if additionally you want the distance and the point Q on the line L, line closest to P naught, you're better off using orthogonal projections.